My name is Shah, and I am part of the wind turbine design competition with Renewable Energy Design. I would like to introduce our members: Amy Shah, Ekta Shah, Nicholas Schultz, and Aditya Shah, me. Um, the main reason that we really want to take part in this competition is so we could aim to create and design a turbine that is both cost efficient and can be used in an urban environment. So more people, we want to have more people become part of this transition. And then it's important to transition, especially to these technologies that kind of force a move away from the fossil fuel industries. Urban setting, so we're going to be considering the University of Alberta, as it has many buildings. We carefully chose parts of the turbine so that we minimize the cost at every location. For example, we had to look around at many suppliers and then consider many parts that could be included, but if it costs too much, and then we have to kind of figure out if it is a worthy item to go inside the turbine and if it really has a substantial effect. Our entire turbine would cost less than 1,500 as per competition requirements, and it will also be able to perform in low wind speeds and be dynamically efficient.
So the group had undergone a number of brainstorming sessions where they built a decision matrix. This helped us to identify which model would be the most suitable one, and we were competing against three major ones, which include horizontal axis wind turbine, which is the three plate, and then the vertical axis wind turbine, the three plate, and vertical axis wind turbine five plate. So from this decision matrix, you can see that the vertical axis wind turbine has a maximum point of 800, and therefore it was selected. Moving on, you can also see from this that the vertical axis wind turbine three blade has more pros over cons in comparison to the other two models. Some of its pros include it can operate at low speeds. It's also beneficial for areas in turbulent wind speeds, making it more suitable for an urban environment. And also, it's cheaper than the others because no viewing mechanism is required, and also inspection and maintenance is cheaper than the horizontal axis wind turbine. So this is our design. So our design includes hub. So we have two hubs. One's the upper one and then the other one's the lower one. We have a thrust bearing here and then six connecting rods, three plates, a disc brake, shaft, generator, and stand. So the radius of the turbine is 900 millimeters and the height is 1850. So this is how our wind turbine functions. So when the wind blows, it's going to cause the wind blades to rotate, and this results the shaft to rotate as well. And then the shaft is connected to a disc brake. So the disc brake will ensure that at high rotational speeds, it stops the motion of the wind turbine. This helps it from causing any damage, and eventually the generator will convert the mechanical energy to electrical energy.
So now I would like to talk about the choice of location. We want to propose to station our turbine at the top of the Tory Lecture Building, which is 57 meters measured from top to bottom. It is about 4 meters higher than the DICE building in the engineering quad. So we want to take the advantage of every extra meter that we can possibly have. The Tory Lecture Building is also the highest building on the University of Alberta campus, which is really helpful because it signifies the importance of that. And so another substantial reason is that the Tory Lecture Building has an existing weather station at the rooftop with live data that is accessible to the public at any given time. And so this will help us get an accurate sense of data on the physical conditions that the windmill is going through. And we could compare that to the performance to evaluate how well it's performing at any given moment. So for functionality, I would like to first off mention that we used QBlade to do all the simulations. For example, we have the tip speed ratio graph and the velocity, and then the power graph and the velocity. We can start off with the TSR versus the velocity graph. We can infer that as the velocity increases, the tip speed ratio decreases rapidly. And so we assume the average velocity at the top of the Tory Lecture building to be about 4.4 meters per second, which means that the tip speed ratio will be really high, which is a really good thing. And from the second graph, which is the power in watts versus the velocity meters per second, we can infer that the cut-in speed is about 3 meters per second, which is approximately 10 kilometers per hour, which is relatively low, especially considering that the windmill is going to be stationed at the top of the Tory Lecture building. And so this means that the dynamic efficiency will be really good because it can start moving at at really low wind speeds. So I want to talk a little bit more about the functionality. So first off, the airfoil shape is NACA 63209, and the radius of the blades is 0.9 meters. This is the maximum possible radius because we want to maximize the torque and from the limitations as well. The chord width is 0.3 meters from this side to there, and the length is 0.85 meters, sorry, from top to bottom, also the height of the blades. And I would also like to mention this was done through Q-blade as well.
So for structural durability, we obtain the stress and strain. We use SolidWorks to get the data. The yield strength of the material is 2.757 times 10 to the power of 7, which is very high. And our max value is just 5.018 times 10 to the power of 6, which is less than the yield strength. This makes the material and the blades very strong. And yeah, as you can see, this is an expanded view of this section, and that section is the bolt holes. So, and that is a section where the maximum stress is felt. Now for the strain, the model has very small strain values. As you can see, it's times 10 to the power of -5 times 10 to the power of -10. This means that the blades will not deform easily. And yeah, so that means that the model is feasible.
Vertical wind turbines tend to have a simpler electrical system compared to their horizontal turbine counterparts. And this is due to no rotation of the actual turbine being necessary, as it's always facing the wind. Our power will be produced by a 200 watt 12 volt generator, which can rotate it up to 900 RPM. And we'll get to the 900 RPM through our gearbox. Our generator then sends power through a capacitor to regulate the voltage, which is followed by an amp meter. Our amp meter will be used to detect whether the generator is at or above its capacity. And if it is, we'll initiate our braking system to prevent damage or fires from occurring. The internal electric circuits have an efficiency of approximately 99.8%. The generator has an efficiency of about 68%, given its low wattage. The overall efficiency of the electrical system is determined by multiplying these two numbers together, and we get an efficiency of about 68% overall.
For efficiency and power calculations, the power input obtained is 79.8 watts. These two graphs were obtained using SolidWorks flow simulation, and they helped obtain the value of CP, which is 32.35%, which is the turbine efficiency, and the total efficiency was also obtained, which is 32.06%. The total efficiency is less than the turbine efficiency. This is because of mechanical losses and electrical losses. And finally, the power output is 25.28 watts. More detailed calculations can be found in the proposal.
So next up, noise simulation. I would like to mention that the noise simulation was also done using Q-blade. So to begin, since the height of the Tory Lecture building is 57 meters, a person walking by around Tory can assume to be 60 meters. So when we're doing our simulations, we put the distance from the turbine for the observer to be 60 meters. And so we can infer from looking at the graph that the average sound the person would hear is about in the range of 40 decibels, which is approximately the level of approximately the noise level of a quiet conversation. And so this will practically be barely audible to the person, considering that there will be many other noise sources around the area. Furthermore, we did a noise simulation for maintenance workers who will be working in close proximity to the turbine, about a distance of roughly 1 meter. And we get a graph from here in which we can infer that the maximum value is around 75 decibels. This is approximately the noise level of a passing train, which over time can be quite loud. So it is recommended that anyone working within close proximity of the turbine wear any hearing protection. So next up is the cost analysis. We calculated the cost in 3 different parts. And so first off, we calculated the cost of all the materials that are needed to build the turbine, especially the aluminum alloy 6061. We got the price per LB from a supplier in Edmonton, and then we can find the volume of the parts of the turbine from SolidWorks. And then so using those two things, we can figure out the total cost of all the materials. Next is we calculated the cost of all the other components that are needed, like the generator and the disc brakes. We have it summarized in a little table here. There's the name, the supplier, and then the cost. Thirdly, it is assumed that the mechanic shop will take around 2 hours, which will cost around $100 because they charge $50 per hour. There will be 4 people from our group helping. We're assuming 2 people from the mechanic shop, and then approximately maybe 2 people from the red team. And so that makes 8 people, and so then we would have 16 man hours. And when we add up all the costs, we get the total cost of the wind turbine to be 1,407, which is below 1,500. So that's a good sign.
So we had a couple problems when it comes to safety factors for our wind turbine. Considering that our wind turbine is made out of aluminum, we were concerned about the buildup of static electricity throughout our turbine, which could have a huge discharge. So we decided to cover it in glass fiber sheets to prevent the build of static charges. So what this does is essentially grounds static charges before they're even allowed to build up, and prevents it from traveling from the blades to the stands. Another problem we had is that we were concerned about bird deaths, as these do tend to be caused in large number by wind turbines. So to prevent this, we decided to paint our windmill yellow. And this is in an effort to deter birds, as they don't appear to like the color yellow very much, and it also happens to be one of our school colors. Efficiency is hard to increase on a vertical wind turbine. This is largely due to one of our total of 3 blades always causing drag. That's the big advantage of a horizontal wind turbine over a vertical one, is that all 3 blades will be producing power. In our case, the main source of inefficiency was this one blade causing drag. To maximize our efficiency, proper maintenance and lubrication is what's needed. Another way to maximize efficiency would be to create a curve in the blade. And this curve would allow us to catch the wind better and create a larger cross-section to the wind, and thus create more torque and more power. Another way we could do it is by making the blade system wider. This also has the same effect of creating more torque and producing more power overall. So one of the major philosophies or foundations for our design process was trying to keep the cost as low as possible. And in this case, we were mostly focused on keeping the cost low over the long term. So over the course of 20 years, keeping the cost low. And to this effect, we decided that we wanted to build it with high quality parts, which would be high cost at the beginning, but reduce maintenance costs in the long term. So in this regard, it would be hard to reduce our cost anymore. It's our vertical wind turbines got the minimum parts needed for it to function effectively. We could reduce the cost by removing 3 of our 6 connecting rods and the upper hub from our design, and this would save us about $80 overall.